in unconsolidated material. You can put in sheet piling walls. You can put in what are known as funnel and gate systems where you channel all the water to one place. You can put in permeable reactive barriers, which are basically trenches filled with reactive material so as the water flows through it, it gets cleaned up. There's lots of cool things you can do when you can dig a trench or when you can pound a sheet pile down into the sediment. We don't have that luxury in Bedrock. So the best that we can do is you can sort of create a barrier by injecting grout into the fracture. So if you have a small source that you're trying to control, a very focused source that you're trying to control, you can pump grout into the fractures to prevent water from flowing quickly through that. So you can create a temporary barrier, and then you can pump water on the inside of that, so on the plume side of that, and it helps you control your source. Not done a lot in fractures because, like I say, you can't really grout up a whole mountain. All right. The technology is there. We use it for tunnels when you put in a tunnel for a subway or for cars. They often will inject grout to reduce the seepage into the tunnel, but it's not going to work over very large areas. Similarly, you can create collectors, or sort of like the closest we can get to a trench in bedrock. In shallow bedrock, you'll see these what's known as blast trenches. So they drill a bunch of holes and they put explosives down there and they blow it up, and the rock just breaks up, right? So this creates a high permeability wall, and then as the groundwater moves and hits that wall, it'll flow to a central collector, and then that water can be pumped out. Okay, so it's sort of a barrier, not a barrier, but a perimeter that you can put around a contaminated area. But again, these are very hard to do on very large scales. This works best for shallow, focused areas. Hydraulic fracturing can be done in much deeper systems. So you can drill a well and then hydraulically frack and increase the permeability. And this is done all the time in the oil industry and the gas industry, where they drill a well and they pump fluids in, and that causes a hydraulic pressure in here, and that it can propagate fractures farther out, actually create new fractures, and it can cause connections in fractures. And so even very tight formations like shale, they're able to get gas out of now because they drill wells, they go down horizontally, and then they hydraulically fracture them, and they create all this permeability that didn't exist before. So the hydraulic fracturing has been around for a while. What's kind of new is the ability to directionally drill, so you can sort of break open places that you weren't able to get to before. So the general idea is you're going to increase the pressure here, force fluid in there, and open these up. In the oil field, they use proppants to keep the fractures open once they're open. But the general idea is you want to increase the permeability. And this allows you to extract more fluids than you would be able to extract in the natural formation. So this is used in conjunction with some of the other techniques that I'll show you, and I'll point that out. Again, this is just an illustration of the blast trench. You can see how this would be a fairly shallow technology. So you're drilling in a bunch of these wells, and it's very impressive. Boom, and the rock goes flying all over the place, and it's quite satisfying. But it's going to work best when you're working with pretty shallow sources, and especially those sources that can't get under this wall. And again, this is an illustration of how this might work in a vadose zone. So you have you're injecting air this time, and you're doing the same thing. You're creating a pressure inside the fracture, and that's overcoming the confining stress, and it cracks, and that allows you to get more air through here to circulate the volatiles out of the rock. Okay, so in situ treatments, those are kind of methods for getting at ex situ treatment. So mostly what we're trying to do is, in those illustrations, is to pull fluids out, pull vapor out, and treat it. What we'd like to be able to do is just treat this stuff in place, right? because once it's out, if it's fluid, it's going to have to go through a treatment process, and where's that going to go? Where's that water going to go? Where's the stuff you extract going to go? It's got to go in another landfill somewhere. So it'd be nice if you could treat it in place, and we don't have to worry about extracting it. So one way to do that is to, rather than pull the water out and treat it, we inject reactants into the formation to try and degrade it in place. So chemical oxidation, there's a number of chemicals out there that can be used to oxidize VOCs. And these are just some examples. Ozone peroxide, hydrogen peroxide, the basically concentrated version of the stuff that you buy at the drugstore. Fenton's reagent, which is hydrogen peroxide with iron, those two react and they create a very oxidative state. Permanganate, which is this molecule here, and it just happens to be because of the valence of the manganese, it can react or participate in a lot of reactions and cause oxidation. So there are other things that you can inject as well, but the general idea is we're pushing something down there and trying to get a reaction to occur in place. So obviously you've got a lot of the same problems that you had before. Before you had to extract the fluid, now you got to get this stuff down. So again, you're limited by your permeability. Here's an example of TCE contamination in a sedimentary rock and a shale bedrock at the Allegheny Ballistics Lab, where they injected permanganate into wells. And this is again, they had a source zone that they were trying to take care of. It was fairly focused. They knew where the stuff was, and so they were able to inject this oxidizing chemical into the formation and cause destruction of the TCE. And here's the tanks of it's this purpley looking stuff. Thermal treatment. This is what we all would like to see, right? We just like to just blast that stuff out. And, it'd be nice if we could do this. And I was telling Tom earlier back in, I don't know why the expression in the Niagara Falls area is, well, this is the best we can do until some Star Trek technology comes along. So you can do some heating of the rock to try and destroy this stuff. You can use a steam, an electrical current, radio frequency. But you can imagine trying to create radio frequency is basically a microwave, right? So trying to create a microwave heating area over large distances is going to be challenging, right? They tried steam at Loring Air Force Base in Maine. They had a TCE plume, and they injected a tremendous amount of steam. This was a very well-studied site. It was a research site. It was a technology proving ground, essentially. And they couldn't quite get it to work because the permeability was so low that they didn't get good connectivity among the wells. Okay, Edwards Air Force Base, for example, this worked better in a granite. They had a little bit more permeability, and the thermal constraints were a little bit better, so they got better heating. But the best they could do at this particular site was they got it up to about 50 degrees C. And that actually helped because it increased the rate of biodegradation, it increased volatilization. Of course, they're in Maine, so the rock otherwise is really cold. Here, I'm not sure, going from 20 to 50 is going to make quite that much difference, but it definitely does help and stimulate some of these other processes if you can't just destroy it. So I'm not saying that steam doesn't work, but there are certainly challenges with it. The radio frequency is a little bit more interesting because basically it's only heating up the water. Just like your microwave, it heats up only things with water in it, right? So again, it's a short distance kind of thing, but at least it's attacking the fluids, which is what ultimately we want to do. So if you have pretty tight matrix rock, so there's not a lot of water in the pore space, this is going to work a little bit better because it's only the energy is going to go just to the fractures where all the water is. Bioaugmentation, biostimulation. I'll get to natural biodegradation next, but why wait around for the bugs to do their thing if you can stimulate them, right? Let's create new microbes that are capable of destroying all this stuff. And this was a huge topic in the 90s. People were running around with all kinds of proprietary microbes that can eat this and destroy this. And then the EPA was worried that it was going to eat all of our car tires. This stuff is going to get loose. I'm not kidding. It's going to get loose in the atmosphere, and then all of our tires are going to rot off. And so people became worried about these superbugs. And some of these have found applications in oil spills. They use these things in oil spills. But more commonly, they're a little bit limited in groundwater because what happens is you get a limited number of these microbes down into the ground, and the natural fauna tends to sort of overtake them because they're not adapted to the specific chemistry, or they're not optimally adapted to the specific chemistry of the groundwater. So it does work sometimes. I've seen a lot of failures on this. And usually the reasons that they give is because they didn't quite understand the chemistry, or there were some other microbes that took over, or it turns out there's some amoeba that just grew up and ate them all. It's nature, And so you go and you try and create new nature, and you have to live with the results. What's a little bit more popular is let's work with the bugs that are down there. At the same time people were developing all these microbes, there were biologists that were going out and finding out that there are microbes everywhere. I mean, on the highest mountains on the planet, in the deepest wells that we could drill for oil, they were finding bacteria. And most of the time, there's already bacteria that are capable of degrading these things. It's just they're in very small numbers. If given the right conditions, given food, and so, essentially we need nutrients and electron acceptors to make all this work. Given these conditions, these bugs will grow up, and then they'll start to degrade contaminants. Okay, so if you can stimulate them a little bit more by giving them a little extra carbon to work with, giving them the right geochemistry to work with, that you can actually stimulate the natural fauna to degrade. This is, I couldn't find a sediment, I'm trying to stick to sedimentary rock, but I couldn't find a good example for at least a well-studied site of biostimulation. So I went to the Snake River Plain, which is a basalt. These are lava flows, and they injected lactate as an electron donor. And so what these bugs are doing is they're transferring electrons. This is how they get interest or energy. They're either taking an electron off of well, sometimes we talked about last time, you can get co-metabolism. So sometimes they're not even trying to eat the stuff that we want them to eat. So they're not trying to actually destroy the TCE, for example. But if they're in the process of degrading something else, they'll create enzymes that, in the process of destroying this, in this case lactate, they will create enzymes that destroy the TCE as well. So they did this in this basalt, and this is an interesting geology because this is essentially a lava flow on top of clay. So you've got hard rock on top of clay, but this is pretty impermeable. So they had, it was very thick, it's 200 feet, but at least there was a bottom of this that they could work with. So they injected some lactate and managed to degrade the TCE to some extent. So here is the plume before they injected anything. You can see they had a very focused source at this particular site. They had high concentrations in these wells, and this is where they injected the lactate. And over time, the bugs did very well destroying the TCE. Oops, thought I had more. And so, and there are some successful examples of using biostimulation to degrade TCE. Monitored natural attenuation. This always makes people nervous because they think it's, people are walking away and saying, oh, you're not going to do anything, you're just going to leave it in there. But it's not a do-nothing approach. The key in this technology is monitored. You have to be able to assure yourself that that the plume is not going anywhere, that the plume is beginning to degrade on its own, that the natural fauna are beginning to degrade the plume. And if it's happening on its own and you can assure yourself that it's not going anywhere, why not just sit there and watch it go away? So, this has become more popular and used more often as people have become more confident that it works. But again, you have to assure yourself that the monitoring is going to work. And as we discussed in the last talk, this can be difficult because fractures, the flow in fractures is complicated. It's difficult to monitor. So I want to try a little experiment. This is a 10 by 10 square area where we actually measured a plume. In this case, it was just salt water. But we used radar to actually track how it moved. And so we injected salt water in this well, and then we used radar, and I'll show you a graphic later, but we used radar to plot where that salt water went. Okay? So what I need is somebody with a steady hand to help me. You want to try? I want you to place a monitoring well somewhere in that white zone there. Right there, all right? Right at the tip of that. Anybody else want to try? I need a few more monitoring wells. You want to try? All right. Where do you want to put a monitoring well? Up here, all right? Anybody else? You guys have steady hands. Oh, where'd it go? You got to push the little red button there. There we go. Oh, okay. Wow. You guys engineers or something? One more? One more for fun? There you go. The little red button in the middle.
Oh, okay. Oh, I'm getting back into it.
Don't shoot me. You got to be in the white part, though. We didn't measure that part over there. Okay, right over here. There we go. Oops, I lost it. That one collapsed. It was right there.
Over to the side more, closer to the, yeah.
I lost my sticky. Where was it? Over here?
It was over toward the middle of that, right about there.
Oh, over here. Oh, you're going right to the source. See, that's cheating. You know exactly where it is. All right. So let's, oops, I need that to advance the slide. You guys have steady hands. It's always painful to watch you go to these meetings, where your students are giving presentations. And you can see on graph A. All right, so let's see how you did here. Wow, we got, looks like we got a majority of hits. We've got, let's step back here. Looks like that one hit the plume. That one hit the plume, if you can call it a plume. And this one got it, this one missed. So that's pretty good. You got 3 out of 4.
Which is the color?
Oh, I'm sorry. The green is the saline and the I've been looking at this for so long. The green is the saline fluid and the blue is the background. Okay. And again, this is over a pretty small area, and we knew exactly where we were injecting it. And how do we know this? Well, this is a bedrock fracture. It was.
You want up there stuff?
Huh?
You want those up there?
Oh yeah, I guess I should get rid of those.
Oh, that was too.
Damn, they're hard enough to stay on there. So this is a bedrock fracture. It was a single fracture, and we injected only in that one fracture, and it was basically horizontal. So when we went back and forth with radar, the radar reflects off of the saline fluid, and so we could see where it was going. And this phenomenon is called channeling. It happens, and we talked about this a little bit before, but it happens because there is slightly larger apertures than others, and the water is just going to take the path of least resistance. And so these get all connected up, and the water tends to move in these channels. Okay, so if you can imagine now that you have multiple fractures, and some of those fractures are conducting water much better than others, essentially, you're not going to hit, every time you intersect a fracture, you're probably not going to hit the strongest path of flow. All right? So it doesn't mean you can't monitor. It means that it's a little bit more challenging in, why is this buzzing? It's a little bit, is somebody trying to signal me? It's a little bit more challenging in bedrock. And essentially you need more monitoring wells in a bedrock than you would in a relatively homogeneous sediment, because the homogeneous sediment is going to make a fairly nicely distributed plume, whereas water in a fractured medium is going to tend to channelize. And if you happen to sink your well in the wrong place, you're going to probably see a lower concentration than the maximum concentration that's available. So it's not that it can't be monitored. You just have to be careful when you're putting these monitoring wells to make sure that your plume isn't getting passed without seeing it. So this, by the way, is a natural fracture. It's got a 0.5 millimeter aperture. It's a very small fracture. There's nothing unusual about this fracture. All right, I want to give you an example of monitored attenuation and again, we're back in Niagara Falls. Poor Niagara Falls. There's so much contamination to talk about. This is an aerospace site contaminated with the TCE. Oops, there we go. It's in interbedded dolomites, limestones. There's some siltstones in there, a little bit of shale mixed in. But I should have brought back that picture that I showed you last time. What you have to realize is that these fractures are very irregular. They're bedding plane fractures, and the beds are dipping about 2 feet per mile, so it's almost completely flat. And most of the water is moving through these bedding partings. Okay, so if you drill a hole, here, and you find that you've got permeability here, then if you find the same place in the strata over here, you're probably going to have permeability there. So my point being that this is a very simple site as far as bedrock goes. Okay. So we have a situation where people had a bunch of, they're using TCE, they were testing jet engines, and they were dumping it into a pit, and they put a cap on it, but it still leaked down into the bedrock, and that formed a plume. And so this is an image of the plume from Dick Yeager's report. This is a very nicely documented report from the USGS. So here's the original source, and obviously the water is moving down in this direction. And you can see that a bunch of wells were put in trying to track this plume as it moved down gradient. It's essentially moving in this guelph formation, which is a sort of a fractured zone. The microcosm studies, which is you take the native soil, you take the native water, and you mix it together, and you spike it with TCE, and you watch whether it degrades. The microcosms show that the TCE should degrade, and then that's going to form the CDCE, the cis-DCE, as a daughter product, and from that, vinyl chloride, and then finally ethene, which is what we want to get to because it's non-toxic. So it looked like there was potential, using water from this well here, that there would be some significant degradation. And as it turned out, that was absolutely the case. Here's the TCE plume, and this is the DCE plume, and then finally the vinyl chloride. And you could track the progression of degradation at the site. Now I should note that they're collecting water here, so they don't want the plume to move off-site. So they were actually extracting water here. But they weren't stimulating, they weren't doing anything else. They were just making sure that the plume was contained to give it enough time to degrade. Now there's a lot of carbon source in here which helped. It turns out there was natural hydrocarbons in the rock. And so that helped because it means that the microbes were around and the microbes had a carbon source to work with. But this can work, right? It was a little easier to monitor, but this can definitely happen in the natural environment, given the right circumstances. If all that fails, your absolute last resort is to try and just keep it there. And maybe it'll degrade over time, but even if you don't have a hope of degrading it over time, you just try to keep it so it doesn't go anywhere, okay? And I'll show you that's normally done with hydraulic containment. You can't build a wall around rock and bedrock. But it's important to note that the folks that are responsible for this site, that are writing the checks for cleaning up the site, don't like this any better than the people that live around it. And the reason is that that nobody wants to be responsible for a contaminated site forever. They want to clean it. If they could clean it up, even if it's really expensive, they will still clean it up, because no money-making entity, and usually the responsible parties are some sort of industrial site, nobody wants to have that on their books forever, this drain on continuing to pump and treat for eternity. But sometimes it's the only choice. I talked about this site a little bit before. This is, again, from Niagara Falls. And here's the Niagara River. This is the power plant. So the way the power plant at Niagara River works is the falls are over here somewhere. The water is taken in from a tunnel upriver of the falls. It goes through here. This is a power generating dam, and then it discharges down at the Niagara River. So this is a natural gorge. And at this Hyde Park site, they had this unfortunate situation where the contamination, and I'll show you that in a minute, the contamination was moving out to the gorge and actually seeping out into the Niagara River. So people were going down these roads to go fishing. There's a road right here that goes down to fishing, and this stuff was seeping out at the gorge, and it was discharging the Niagara River, and I mentioned before, all this ends up into Lake Ontario. So again, the same geology that I was showing you before, that other site's just down, well, not quite down the road, but maybe like 10 miles away, in another part of the Lockport Dolomite. So they had all kinds of stuff there. It was a landfill. They were taking solvents and PCBs and spent transformers and everything that went in there. And so they had a real soup of nasty stuff. And they also had a lot of it. They had 80,000 tons with 13 million gallons of DNAPL at this site. Right? This is what it looks like over time. As the first thing they tried to do was pump and treat, and all that did was strip the volatiles out of this stuff. And as they stripped the volatiles out, it became more viscous. So you ended up with what was first kind of a viscous fluid, and now is like a tar in the rock. They're just not getting this out of there. All right, unless we get the Enterprise out here to blast it, it's not getting out of there. Here it is on the bedding planes. You see it's moving through the fractures, just soaking the inside of this stuff. And here's where it was seeping out at the gorge face. And this is the road that where the public is walking up and down. In fact, we used to take at University of Buffalo. This is a prime place for taking students to look at the geology of the Lockport. And then they told us we couldn't go down there anymore because there's solvents seeping out of the gorge face. So their first need was to contain this hydraulically. Okay, so what the idea was is, here's the landfill. Oh, geez, I can't even see the landfill area is in there somewhere, but I can't even see it on this picture. But this is the plume from the landfill area. And so the idea was you get a bunch of wells there and you pump it so much that all the water is flowing inward, right? All the water is flowing this way, and then all that water is pumped. It gets, any DNAPL is removed, goes down to an incinerator in Texas. I don't know, all the incinerators are in Texas, I don't know why. And the water itself is treated, and I think I mentioned to you before that they actually run a plant that takes all the stuff, all the contaminated water from this, Love Canal and S area, and it all gets treated at the same place. So this was the plan. This is the ultimate plan. And it sounds simple, right? It's not nice. We don't like the idea of leaving this stuff in here. But actually, it wasn't even that simple. They went for years trying to figure out how to show that all the flow was inward. Because if you put a well in one place in a rock, and if it's not in one of those channels, you're going to get a slightly different hydraulic reading, pressure reading, than if you hit one of those channels. So it looks like the gradient's going in this direction, but really you're just, if you were to put a well right next to it, you would get a slightly different reading. And this is essentially in single bedrock fractures, and it gets more complicated for multiple fractures. So it can actually be quite difficult to show that you have hydraulic containment. And what they ended up doing at this site is using chemistry. I don't want to go into what this chart means, but basically these are the major ions. And one of these is old and one of these is new. This is relatively new water. Okay, so this is water that's recharged, and this is old. And so their thinking is that if that water is pretty old, right, it's not coming down from the landfill out into the surrounding area. So they ended up having to use chemistry to show that they were containing it. And this seems to be working. There's no more seepage at the gorge face, for one thing. And as far as they can tell, they've been able to hydraulically contain the site. And so this is just going to go on forever. They don't have another solution. They're just going to have to pump and treat until the end of time. So I guess I just said this. So they're taking the DNAPL out by sumps and pumps. They're pumping the rest. Okay, so we talked about TCE and DNAPLs and solvents and VOCs. And I wanted to make some mention of perchlorate. We talked about perchlorate transport a little bit last time. We said that it was a salt, dissolves in water, so we don't have any of this immiscible phase to deal with. So, the downside of that is it transports fairly quickly. The good thing is that if you pump it out, you can pull it out with the water. Generally, it's not so hard to pull out. And then once you have the water, you can treat it. And because it's a salt, it can be treated by ion exchange. Basically, these are methods that are standard water treatment methods for any water, drinking water that's extracted from groundwater. So even if you're in a clean system, generally these ion exchange, osmosis, electrodialysis, they'll be used for cleaning up drinking water, depending on the quality of the drinking water. They're not used everywhere. So this can be done. As it turns out, it's quite expensive. It's, for example, in these ion exchange resins, it's hard to get the perchlorate back off the resin. You have to do what's known as recharging the resin. So you've got to find something so the perchlorate gets stuck to the resin, then you put something through that knocks it back off. It's hard to find something that knocks it back off. So it's kind of expensive, but it's really only a problem when you're treating tremendous amounts of water. So you have entire aquifers that are contaminated, and this is a drinking water aquifer. This is a huge problem in the United States because it's difficult to treat those volumes of water. For focused contaminated sites, it's not quite that, compared to other technological problems, it's not quite that difficult. Perchlorate can be bioremediated. This has been shown in ex situ systems. If you can introduce the chemistry that you want and the microbes and all that other stuff, you can certainly biodegrade it. The literature is a little bit sketchy when it comes to in situ biodegradation because there are other compounds that can block the natural biodegradation of perchlorate, but it's potentially possible to biodegrade perchlorate in situ. Okay, so I went back to that database and I looked at all the Bedrock systems. So this is not just solvents in Bedrock, but I looked at all the Bedrock systems that have been remediated that was in that cluin.org database. And I just counted up all the sites where different methods were used. All right, so these are the methods: pump and treat, bioremediation. So this is both, I think this is natural and stimulated. Chemical oxidation, vapor extraction, fracturing, multi-phase extraction, meaning they're pulling out free product. And then finally, thermal. And in many cases, multiple technologies were used. And I think the reason why that pump and treat is so popular is it's usually the first thing that you do before you can think of what your final solution is. You want to hydraulically control, and so you pump and treat. So almost every site has some pump and treat going on. But clearly the big workhorses here are pump and treat, bioremediation, and then this chemical oxidation. This is in situ chemical oxidation. So the Fenton's reagent or the permanganate or the ozone, that kind of stuff where you're oxidizing in situ. In cases, obviously there's a lot of soil vapor extraction going on where you have vapor in the vadose and you're worried about that seeping into buildings. And then a lot of this comes along with fracturing, with some artificial fracturing, hydraulic fracturing, to increase permeability to make all this other stuff work. And there are 7 sites where thermal was used, at least in this database. And I have no way of knowing what this database is missing and how up to date it is, but it looks that thermal is at least being tried in multiple places. So this is not necessarily technologies that were successful. These are technologies that have been tried. So to summarize, there are technologies out there for remediating bedrock. Okay, there's no magic bullet. I guess you probably, as I was going through this list, you're waiting for me to get to the one that's going to just solve all the problems, and I never got to it, and unfortunately we haven't got one for you. There are things that work, but there are also sites where, given all the money in the world, we still couldn't clean them up. All right, I don't know, I'm not speaking specifically about Santa Susana, but the Hyde Park is one of them, right? You could throw all the money at accidental chemical, they got a lot of money, right? They've got some deep pockets, and they have no way of cleaning that site up. They couldn't do it unless they dug the whole thing up and scrubbed it with a toothbrush. A lot of these remediation methods that I showed you work best on really focused areas. So the thermal treatment and even like the chemical oxidation. If you can find a fairly focused source of high concentration, it usually makes more sense to use one of these active methods where you can get in there and just destroy the stuff. Where the more spread out the source is, or the more difficult it is to characterize, the harder it is to use these successfully. And so when you see remediation technologies that are out there that are touted as being, oh, this is amazing, it cleaned up the plume in 2 days, you have to ask yourself, well, is that going to work in my system? In my, just because it worked in a nice glacial aquifer doesn't mean it's going to work in bedrock. And so the remediation goals, unfortunately, have to consider all those things. We go back to the cube. You have to consider what's your goal, what technologies are going to work, and what challenges are presented by the geology, the hydrogeology. So I try to make it a little bit shorter because you were so good with me last time. I don't want to strain your patience. But okay. Questions?
Hang on, Steffi's going to come to
right.
you. And
microphone.
Just while she's walking over there, I said that we would start with a review of the questions that we had at previous sessions. That doesn't make any sense. Let's start with the questions you have tonight, and we'll finish with that. So.
Where the microphone?
My question is, with all the time that's been involved here, 52 years, all right, since the first meltdown, right? That's almost like the tomb of the unknown soldier in your graphics, all right? Problem is, does anybody do any consideration, for instance, in Plant 4 in Japan, you have these spent fuel rods. They're just lying there as a threat. All of this stuff is still up there lying there, and we are in one of the most seismic zones in the world. Simi Valley is fractured. It seems as if management, not you, obviously, but someone at some level is thinking we should go with permanence, the tomb of the unknown. And, I would like to know whether that is a fact. I would like to know whether there is any motivation to do that, because it's not going to work.
To entomb it, you mean, or to completely contain it forever?
I would just leave it, contain it, and keep it there. That's just not going to happen because of seismotomy, because we are going to shake. The rock is going to break. I used to be on federal disaster committees.
I can't speak to what people are thinking because I don't know at the site.
I know
but
you
there's
don't.
a topic that came up last time, and this is the seismic topic. And I'll make that point again, which is we certainly are in a seismic zone, and the fractures up there certainly have been influenced by tectonics. But you got to remember that's happening over geologic time. So, I mean, these over tens of thousands of years, hundreds of thousands of years, there's certainly going to be opening fractures and moving faults and this kind of stuff. But when we're talking about 100-year scales, that's pretty small. And so I wouldn't worry so much about an earthquake making the whole mountain tumble down and releasing this stuff. The fractures are already there. I think we can basically assume that the system that's there now is the one that we're gonna have to deal with. But as to the other questions, I don't know. I can't address them.
Yeah, I wanted to see, what would you like me to write down? Because that's what Matt was able to answer. What other question?
I would like to know whether we are here and whether I have taken part in years of these meetings under false pretenses. You know, at one point we talked about a Superfund site. We've gone through all sorts of things. And as a matter of fact, Southern California is a lot more active than you want to think it is, including Simi Valley, this area, and the San Fernando Valley. The point being, I want to know whether this is obfuscation or not. Whether something's really going to be done. Okay. Now they're talking about a state park up there or some kind of park. I call it glow-in-the-dark park. They're talking about building a subdivision. That isn't the way you deal with things like this.
Okay.
We people are here because we're concerned.
And I really appreciate that you've got some comments that you'd like to make. And I'd like you to save those comments for the comment meetings, because that's important. You'll have an opportunity to do that. What I wrote down is, have we attended these meetings under false pretenses? I apologize in advance if pretenses is spelled wrong. It's this problem when you're writing at a flip chart stand, your typos don't get fixed. But we will take that question. The planning team that's planning these seminars will take that question and we'll get back to you. Okay, I saw Diana up, and then Chris, and then this gentleman here with the red, and then the brown.
Okay, Diana Dixon Davis. Actually, I have a couple of questions, but I'll start with just the first two. First, are there any European models of treating ground rock and groundwater and bedrock, and whether we've learned anything, because contamination there has been going on for hundreds of years in some of the industrial sites, thinking in England and the tanneries and things like that, and I'm wondering what, if anything, has been done there that we could learn from.
There's a nice document that, how are we going to get it to them again?
We're seeking permission still, but by the British, by the UK, they have it's great as just a sort of a general review of solvents in bedrock, but they also discuss some sites in the UK, and yeah, they've got the same problems that we do as well, and they're struggling with the same lack of technology for cleaning it up.
Okay, so maybe we can have that presented at some later point, because maybe they've been doing this longer. I don't know. I'm not. This is a new area for me.
No, I think it's been pretty much going on at the same time. The Canadians are way behind. No,
okay.
But the Europeans are.
A corollary to this is.
But let me clarify.
That was a shot.
We're not going to present the information in that article, but it's an article from the United Kingdom, and on their website they say permission is granted on prior approval. And I've submitted the request, and they very politely told me that they were considering the request, but they haven't responded yet.
But
so
you
as
can
soon as we
download
get
it
it,
from
we'll
their
send it.
website. I downloaded it. You can download it.
Okay, well, then, I will do that. But the corollary to this is, I know that there's a park, a city park in, I think, Copenhagen, where basically there was a major dump with a lot of nasties, and they just sort of covered it up and said, it's parkland.
Yeah.
And that sort of leads into my second question. With the characterization that's going on now, will we have enough information to know at what rate of flow there might be of these contaminants off-site or within the site, so that we could perhaps create a large buffer zone